All right, so chapter 9, we're going to be looking at climate, just what it is, and then focusing mostly on climate change specifically. So it's probably going to be the chapter that I would guess you're probably going to be the most familiar with, just because it's going to be the one that is typically going to be focused on the most in media, and then even maybe just different classes that you've taken in the past. First is with it, we should define what climate is. So climate, we're going to be thinking about the long-term pattern within one region, whereas weather, we're thinking about sort of what's happening in the short term that day, maybe even within an even shorter time period than that. So a couple minutes, a few hours. So just a shorter time frame. So climate, just long term, we're thinking the Pacific Northwest, for example, extremely wet, especially in the fall, winter, springtime, whereas just a certain day in February could be sunny. So that would be the climate versus the weather. And with it, we should think about the atmosphere, because this is going to be the position or the location where this is going to be occurring. And then the different layers within this atmosphere are going to play different roles. But just with the atmosphere, as you get higher up, we've got different layers. So we start with the troposphere. That's where we actually live. And you can see as we go up, if you look, the yellow line starts moving to the left. That's going to be because as we increase in altitude, as we move up in elevation, the temperature is going to be decreasing. And the reason for that is because the air in the troposphere isn't actually going to be absorbing too much energy from the sunlight. What's going to be keeping the troposphere warm is the ground absorbing that sunlight, and then the ground warming the air. So as we get further from the ground, it's just not going to be as effective as warming that air then. So we're going to see the temperature decrease there. But then the second layer, the stratosphere, we're going to see the temperature start to increase again. The reason for this is because we're going to have ozone present in the stratosphere. You may have ozone present in the troposphere at very small concentrations, or hopefully very low concentrations, because it can be harmful to different organisms, so humans, other animals, plant life even. But in the stratosphere, way up above us, we're obviously not going to be breathing this air. So what the ozone does in this layer is actually protect us from some of the harmful UV rays of the sun, which can damage DNA, cause mutations that way. And that's why we see the temperatures start to increase, because in this region of the atmosphere, ozone is actually going to be absorbing some of that sunlight. So it's going to be gaining some of that energy. Essentially, we're going to see the temperature increase. Whoops. And then mesosphere, again, we see it decrease because we don't have anything actually absorbing the sunlight, really. And then the thermosphere is finally, we see the temperature increase quite a bit, because in this region, we're going to see the different gas molecules are going to be absorbing extremely high energy sunlight. And essentially, they're just going to be breaking down into ions, but it's going to be extremely, extremely high temperature. But with this, it doesn't mean it's going to be, it wouldn't feel very warm, because in this region of the atmosphere, there's going to be very, very little gas. So even though the gas particles there are going to have a very high temperature, since there's so few of them, there's going to be so little heat overall located in that region of the atmosphere. And then in addition to just the layers of the atmosphere, we want to think about the movement of the air within the atmosphere. And again, we're thinking specifically of the troposphere. Just because that's going to be where we live, that's going to be the weather that affects us the most. And then the other regions are just going to be more sort of stagnant than the troposphere. So these are going to be sort of more calm layers of the atmosphere, the higher up ones, especially the stratosphere. But with it, we can see the currents here, showing the convection cells, the way the air in the atmosphere is going to move. And what's happening here is essentially just the movement of the air as it warms. So if you think about the equator, going to be a relatively warm location. So the air there is going to get hotter. It's going to increase in temperature. And when it does that, it's going to become less dense. So it's just going to rise. That's what we're going to see occur here. But then as it rises, it's going to start to cool. So that's why it's going to then just drop again. So that's why we see these different convection cells. And you can see they're pretty much the same in both hemispheres, just in opposite directions as we move either up away from the equator in the northern hemisphere, or down from the equator in the southern hemisphere. Oops, and I meant to put this on the previous slide, so I meant to have these in the reverse order. But again, just thinking about the thermosphere, the top layer of the atmosphere. Like I said, it's going to have very high temperatures, but the reason it's not going to have a lot of heat in that layer of the atmosphere is just because there's not going to be a lot of atoms. So the few atoms there are going to have a high temperature, but since there's going to be so few of them overall, there's going to be a little so little heat located in that layer of the atmosphere. And then with climate change, what we're looking at, what often gets focused on is going to be the greenhouse gases. And what's occurring in that situation is the sunlight just comes, hits the surface of the earth. That could be land, that could be different plants, that could be the ocean, that could be snow. But depending on what that surface is, it's going to absorb some amount of that sunlight. It's going to reflect a certain amount of that sunlight as well. So what we see here is we have the sunlight hit the surface, some of it gets reflected off, and then it's going to get reflected up back into the atmosphere. And some of these gas molecules are then going to sort of reabsorb that sunlight. And that's what we're seeing with these greenhouse gases. That's how they're warming the atmosphere. They're absorbing the reflected sunlight, and then they're taking on that heat and redistributing it into the atmosphere. And you can see what some of those greenhouse gases are here. So we've got carbon dioxide, water vapor even, and then methane. So carbon dioxide and methane are probably the two that get focused on the most. And then there are a few other ones. So if you look here, nitrous oxide, going to be another big one. And then fluorinated gases. So you may have heard of CFCs, chlorofluorocarbons, hydrofluorocarbons, so substances like that are used in refrigerants, can get into the spray cans as well, can get into the atmosphere, and then do the same thing that carbon dioxide does. And then some of these, you can see, are even going to do it in a sort of a much more efficient manner in terms of warming the atmosphere. So it'll be even worse in terms of the greenhouse effect. Because you can see with this, the GWP, just the global warming potential, just essentially how much is that gas going to warm the atmosphere. But carbon dioxide gets focused on the most just because that's going to be the one that gets produced in the greatest quantities, although methane is currently getting produced at a faster rate. So there is much more carbon dioxide, but the increase is occurring faster with methane currently. And then one other factor to the climate is going to be just evaporated water itself. And the reason this is going to be important is because, one, it's going to affect the distribution of water. If something evaporates, it's then going to be able to travel through the atmosphere and then come down as precipitation in another location. So that's how we can move the water around. But another thing that's going to occur when we have that process take place is we're going to be redistributing heat as well, because the process of evaporation or condensation, just the reverse, is going to be an energetic process in one way or the other. When it's evaporating, it's going to be sort of taking that heat. And that's what we're going to be referring to as latent heat, because now that water vapor has that energy just sort of stored in it. But then when it condenses, when it comes down as precipitation, it's going to be releasing that heat. So just like it's redistributing the water, it's going to be redistributing the energy as well. And this is going to be important for especially things like hurricanes that are going to be reliant on this latent heat. That's what's actually sort of supporting the hurricane, supplying that energy is going to be this latent heat. And as we see global warming occurring, we're having more evaporation. So we're just having this, so sort of having more water vapor in the air, we're having more of the redistribution moving of that heat and that water. So we're going to see changes in the weather patterns as well. And that's why you're also going to see increases in hurricanes. And then we talked about the convection cells, so the movement of the air currents. But another thing that's going to affect the climates is just the ocean currents. And these ocean currents are going to affect the climate of climate on land. So if you look at the over to the left here, the North Pacific current going down into California, so up kind of near Alaska down into California. This is going to be bringing colder water. So that's going to be why San Francisco is going to stay a little bit cooler. The northern part of California is going to stay a little bit cooler than the southern part because of that. And then kind of the reverse, the Gulf Stream going up from the Gulf of Mexico up towards Europe. That's why the locations in Europe are going to be much warmer than similar locations in Canada, because this Gulf Stream is going to be supplying heat to those locations essentially. And then this process is going to occur because partially because of the wind. So the wind is going to move the surface water. That's going to give us surface currents. And then with the movement of those surface currents, as well as the differences in temperature of the water, differences in the amount of salt in the water, that's going to affect the currents. And that's going to give us the different currents we see here. And again, these ocean currents are going to heavily influence the climates on land as well. And then with climate, climate change is a totally natural process. And the way they actually observe this is by looking at ice cores. So just sort of digging a long tube out of the ice, taking it up, and then within those ice cores, they've got air bubbles, which essentially just trap sort of samples of the atmosphere. So the further down in the ice you go, just sort of the further back in time you're traveling, in terms of actually sort of looking at the concept, or the composition of the atmosphere at that time. So what they're able to do is look at those air bubbles, see what the concentration of carbon dioxide was like. They can get an idea of the volcanic activity based on the sulfate concentrations, and they can actually get an idea of the temperature, because what they can look at is the different isotopes of oxygen. So remember, an atom, the element composition of an atom is determined on the number of protons. But you can have a different number of neutrons and still have the same element. So oxygen, you can have oxygen, you need 8 protons. If it's got any other number of protons, it's not oxygen. But you can have 8 neutrons, you can have 7 neutrons, you can have 9 neutrons, so you can have a different number of neutrons. Those are just the different isotopes of oxygen. So what they were able to do is look at the different isotopes of oxygen in that sample. And then based on the ratio of those isotopes, they're able to determine the temperature, because those isotopes are actually going to evaporate at different rates. So they were able to back calculate sort of how much evaporation would have taken place, what that temperature must have been, and determine the temperature that way. So they were actually able to get a pretty good understanding of what the atmosphere, what the climate was like, just based on these ice cores. And then with this one, so this is not based on an ice core. This is not going back too long. So this would actually have been measured directly. But you can see the blue ones are just the years where the temperature was below the average global temperature throughout the 20th century. Red is just going to be above that average. So we can see lately we've been consistently above it. And we can see that correlates with an increase in the concentration of CO2 in the atmosphere. But if you look at the sort of a longer time scale, you'll see similar spikes. because like I said, climate change is a natural process. We can see changes in the carbon dioxide concentration as well. Although you can see currently we're much higher than anything anything that's been observed in the past from those ice cores. And you can see the temperature pretty similar to anything in terms of the maximum that's been reached in the past. And we'll talk about that a little bit later on. But what has caused the different climate changes, or the different changes in climate, especially the drastic ones? Going to be a combination of things. But even some of the smaller ones we can explain just with the differences in the intensity of the sun. So just the fluctuations in the sort of the output of the sun, that's going to impact the climate of the Earth. And then there's also what's known as Milankovitch cycles, which have sort of three different factors. The eccentricity, which is looking at the Earth's orbit around the sun, which is actually going to sort of change over time. So you can see sometimes it may be circular. In that case, we're going to have sort of a more consistent, more even distribution of the solar radiation. So you'd expect it to be more consistent in that time, the climate to be more consistent in that time. Whereas the more elliptical version, it's going to vary. And then the same thing with tilt, and then just the precession, which is actually just the wobble of the Earth. So all of this is going to impact the amount of radiation coming from the sun, and that's going to be the biggest factor in terms of the natural climate change. And then the big changes here are going to be just sort of a combination of all of these things. So it's going to be just sort of the right mix of these different factors. And then in some cases, you'll also see different things like the Mount Toba supervolcano, which would have been located in what is present-day Indonesia. And then if you have ever seen the Mount St. Helens volcano, this one would have been almost 3,000 times larger in terms of the amount of material expelled into the atmosphere. So what it did was it essentially just blocked out sunlight. And then it only did it for, I think it was 160 years. And I say only 160 just because in terms of the time scale of the Earth, in terms of the time scale of climate, that's typically not a long time frame. But it did lower the global temperature quite considerably for about 200 years almost. Just because there was so much material preventing the sunlight from actually reaching the Earth's surface. And then in terms of just some sort of weather events that we see on sort of a repeating basis, there's what's known as El Nino, or the Southern Oscillation. So this affects in the Pacific Ocean, sort of like South America into Mexico, the western coast of the United States, as well as Canada, and then as well as the other side of the Pacific, Asian countries like like Indonesia. But essentially what happens in most years, you can see on the right, the normal conditions. It's showing the convection circulation. So we're going to have the wind on the surface of the water moving from east to west. And what that's going to do is move the water as well. And as that water is moving, we're going to have the deeper, the colder water replace it closer to South America. And that's going to be the typical weather. That's going to result in the monsoons in Indonesia. But occasionally what happens, and it occurs every about 3 to 5 years, and they're not totally sure why, but the wind pattern sort of disrupted a little. It's not as strong going east to west. So you actually see sort of a reverse almost the water starts moving closer to the Americas. And what we see in that case is just typically quite a bit of storms in those American continents. And then in addition to just impacting the weather, this has an impact on the fishing as well. So the fishing communities in South America, so like Chile, they actually were the ones to kind of observe this cycle because they observed the different patterns within those fish populations. Yeah. So then if we think about climate change, like I said, it's a natural process, but it is currently happening faster than usual. So you can see just on sort of a 1500 year time scale, bounces around. But then in the most recent 150 years or so, we can really see it start to spike. And the reason for that is going to be just the Industrial Revolution, just human caused activity. So what we're going to refer to this as is the anthropogenic climate change, just human cause. So if you think about anthropology, the study of humans, anthropogenic just meaning it's going to be caused by humans. And like I said, just going to be the Industrial Revolution, the burning of those fossil fuels, just the production of those greenhouse gases that are going to trap the energy from the reflected sunlight. And what they've actually sort of observed to help support that claim that is going to be human caused is they have actually measured the carbon dioxide concentrations in the atmosphere. So there's a research station in Hawaii that's set up to monitor the atmosphere. And you can see just in the past, 60 years or so, it's gone from 310 or 315 parts per million. So of every 1 million particles within the atmosphere, 315 of them would have been carbon dioxide. And we can see in the past 60 years, we've gone up to 410. So we've increased about 100, about a 30% increase. And this is going from what was already the highest previous recorded. And then with these, you may be wondering why it's a jagged line. Why don't we see just a steady increase? And the reason for this is just going to be because of the changes in photosynthesis. So in the springtime, around May every year, you're going to see a decrease in the carbon dioxide concentration, because that's going to be when the plants in the northern hemisphere, where there's a lot more land than the southern hemisphere. So that's where the plants in the northern hemisphere, their photosynthesis is going to dominate. So they're going to be using up some of that carbon dioxide in photosynthesis. That's why you're going to see a slight decrease in the springtime. But then in the fall and the winter, when that photosynthesis stops occurring, or at least slows down, depending on where in the northern hemisphere, as well as dying, just plants and other organisms, that's going to release carbon dioxide. So that's why you're going to start to see the increase in the winters, at least the southern, the northern hemisphere summer and winters we're referring to. And again, that's just because the land in the northern hemisphere so much greater than the amount of land in the southern hemisphere. And then the Keeling curve is just what this called. That was just the scientists that kind of helped sort of really focus on this and study this a lot. But there were other previous people that focused on different aspects of this. And the reason we focus on these greenhouse gases is, again, because they're going to be what's sort of capturing the heat that's being reflected, or the heat in the sunlight that's being reflected off the surfaces on the earth, the ocean. It's going to reflect some of it. Snow is going to reflect a whole bunch of it. Even grass, plants are going to reflect some of it. And as we get more of that greenhouse gases, we're getting more of that absorption in the atmosphere. We're retaining more and more of that heat. And what we need to do to kind of prevent that is just reduce our greenhouse gases. And depending on the level to which we're successful in doing that, we can kind of project how much global warming is going to occur. And you can see if we don't really do anything, depending on what source you actually look at, you may see even different numbers here, but we can see a general idea. But if we don't do anything, we can see we're going to get up to potentially about 5 degrees warmer than the pre-industrial temperature. And to put that into context, the global temperature in the previous ice age was about 5 degrees colder. So it's about 5 degrees in the opposite direction. So it doesn't seem like a whole lot, but it is a very, very large difference. And then we can see kind of based on what we're doing, based on what we've talked about doing, going to be 2 to 3 degrees about, at least expected by the end of the century. But what the scientific community is highly sort of suggesting and saying it needs to be almost is this 1.5 or 2 degrees. Once we sort of get above that, we're going to see much more severe consequences. But again, with these greenhouse gases, carbon dioxide gets focused on a whole bunch just because it's the largest in terms of the amount of it in the atmosphere. But the other greenhouse gases are going to be very important as well. And if you look, you can see the parts per million again. You may be wondering why the percentages don't really match up. So carbon dioxide, 394. The rest of these very small numbers, but there's still relatively sizable percentages. It's going to be because these different greenhouse gases are going to absorb energy differently. So carbon dioxide is going to make up the biggest portion just because there's so much of it. But these other greenhouse gases, even though there's relatively so little of them, because they're better at absorbing that energy, that's why they're going to have a larger effect relatively. And even with carbon dioxide, that's like I said, the one that gets focused on the most. We can see an increase similar to carbon dioxide for these other greenhouse gases as well. So methane, nitrous oxide are going to be produced during similar processes related to just expansion of fossil fuels, expansion of livestock, just this expansion of sort of humans and just resource consumption in general. And then what this is just showing is, if you look, we've talked about it a little bit, the reflection of radiation off of the different surfaces on the Earth, so snow, land, water, whatever, even human-made structures are all going to reflect sunlight at different rates, different levels. But just the albedo is what we're looking at there, the reflection of that radiation. But the reflection is going to be a different wavelength than what's actually coming in. The reflection is going to be the IR radiation. So what we're looking at here is the wavelengths that these different substances are going to actually absorb at. And you can see ozone going to absorb in the reflected spectrum. Same thing with carbon dioxide, not a whole bunch, but still going to absorb there. Water as well. And then if we had the other greenhouse gases on here, methane, the fluorinated compounds, we would see peaks in here as well, because they're going to absorb in that region of the light that's being reflected. And that's why they're going to be greenhouse gases. If they didn't absorb in that region, we wouldn't have to worry about them, because they wouldn't be able to sort of capture that light, capture that energy, retain that heat, and keep it in the atmosphere. It would just sort of just pass on through, head right back out into space. We wouldn't have an issue with it. But because they do absorb in that wavelength region, that spectrum, that's why we do see this process occur. But I should also mention, just like climate change is a natural process. The greenhouse effect is a natural process. If we didn't have that occur, the global average temperature, instead of being like 15 or 16 degrees Celsius, it would be like 0 degrees Celsius, maybe a little cooler. So we do want the greenhouse effect. Does help keep the earth warm. It's just we're seeing it get sort of out of control. We're seeing the greenhouse effect occur too much now. And then with methane, like I said, we didn't see it here, but if we included methane, we would also just have a spike somewhere in this region, because that's where it's going to be absorbing the reflected sunlight that's bouncing off the Earth's surface. It's much better at absorbing that reflected sunlight than carbon dioxide is. It's not as prevalent in the atmosphere as carbon dioxide, but it's better at absorbing it. That's why we do have to worry about it. And like I said, there's a whole bunch of different sources from it based on different industrial processes. So mining and fracking releases it. Landfills is going to release it into the atmosphere. Pipelines just leaking it. Livestock produce it, so you have cattle especially. But one unexpected source is actually going to be from dams. So a lot of the times dams are used for hydroelectric, so they have the water supply. But what that's going to cause to occur is just the buildup of biological material at the bottom of those dams. That's going to result in the production of methane, which is then just going to get released from the water. So there's actually some dams used for hydroelectric energy that produce much more methane. So they're having a much larger negative impact on the environment from the production of methane than they are from the clean production of the electricity that they're actually producing. So the methane, like I said, can come from a whole bunch of different sources, but one sort of unexpected one is just the dams in some cases. And then, like I said, there's different projections on where global warming is going, depending on how successful we are at curbing the carbon emissions, because that's going to determine exactly how much global warming takes place. And 2 degrees is kind of the threshold. Really 1.5 degrees is what it should be, but 2 degrees especially. If we get above 2 degrees in terms of the increase from pre-industrial temperatures, we're just going to see the continued and worsening consequences that have already taken place. So we've already seen wildfires. We're just going to see those continue. We're going to see them increase in frequency, as well as the potential for destruction, so just the size of them essentially. Similar to that, we've had droughts, desertification, just large heat waves. So I wasn't here in the summer last year, but the heat wave that came to the Pacific Northwest sounded pretty crazy. But then also just in Utah, where I used to live, there's just, in the summer, it used to rain for like, it seemed like 12 minutes, like maybe once every 2 months. And then they had to have restrictions on when people could kind of water their lawns and things like that to conserve the water. That's going to impact soil quality. It's going to impact the food production. We talked about a little bit ocean acidification, just the absorption of that carbon dioxide leading to more acidic conditions. That's going to worsen the marine environments, especially for coral and the different organisms that rely on that for sort of the structure for their ecosystems. We're going to see the continued decrease in the amount of ice caps, glaciers. That's going to increase the sea levels, which is going to lead to climate refugees. Same thing with the loss of farmland. And then all of that's just going to lead to the increased, at least for potential conflicts, even leading to wars. So there's a whole bunch of negative consequences for global warming. And then just looking at one of them, what we're going to see is most of these are going to be sort of positive feedback loops, in that the negative consequence is going to lead to more of it. And just with the melting ice in the North and South poles, if we look at what happens, the temperature increases. Obviously, we're going to see the ice melt in that case. What that's going to do is, as we have less of that ice, we're having more of the water exposed. So the sunlight's going to be absorbed more now. We're going to see more of an increase in that temperature, just because we're having more of it absorbed. We're retaining more of that heat in the ocean. So we're going to melt more of the ice, and we're just going to see that process occur more and more. And then in addition to that, what we should also mention is when the different pieces of ice, when the snow caps, things like that, when they actually melt, in addition to just causing the sea level to rise, they're also going to be releasing just carbon dioxide, because the different glaciers, snow and things like that are actually just going to sort of serve as a place that can capture carbon dioxide and just sort of retain it, rather than having it floating in the atmosphere. But once the snow melts, that carbon dioxide is just going to get released. And there's a whole bunch of carbon dioxide that's actually stored in the North and South Pole. So in addition to seeing this process, this feedback loop, what you can also think of it as is a carbon dioxide greenhouse gas feedback loop. Because as this snow melts, it's going to release more carbon dioxide. We're going to see an increase in temperature, going to cause more ice to melt, release more carbon dioxide, cause an even larger increase in temperature, and then just sort of see that process occur over and over again. And then with climate change, obviously we've got to do something. If you look at the right here in red, you can see the cost if we don't do anything in terms of the damages that are going to be related to climate change, and that includes damages to structures, loss of life, sick days, the cost of sick days and things like that, just a whole bunch of different factors. You can see in 2100, or by 2100, about 20 trillion. By 2200, though, up to 70. And that's if we don't do anything. You can still see it's going to be pretty substantial no matter what. But if we do enact policy, we can reduce that by about half in by 21. And then even slightly greater than half by 2200. And then similarly, the extent to which we're able to effectively slow climate change, because we're not going to stop it at this point, really, but we can slow it. And the sort of the cap we put on it, again, should be 1.5. 2 is kind of the limit, and we can see just sort of the larger effect as we get further past that. So when we get from 3 degrees to 4 degrees in terms of the average global increase, that effect is just going to get, in terms of the cost, is just going to get extremely large. It's going to double just from that 1 degree increase, essentially. And with this, we want to think about who's going to be affected the most. And not surprisingly, it's going to affect the poorest communities, and specifically the poorest communities in Africa and Asia and South America. Just like everything else we've talked about, poorer communities are just going to be less able to sort of withstand whatever these different stresses may be. And the reason for it is because the richer countries, if it's coming down to food shortages, the richer countries are going to be able to buy food just because they're going to have more money. If it's coming down to quality of water and things like that, the richer countries are going to be able to build purification systems and things like that. They're going to be able to import different resources, so they don't have to destroy their own land. Whereas the poorer communities are going to just continue to be exploited. and then they won't be able to sort of advocate for themselves. So it's just going to be sort of the continued thing we've talked about for a while. And then in addition to that, we also have to think about the intergenerational equity, just thinking about the future generations. And essentially just if we don't do anything, what quality of life, what shape is the earth going to be when it's their turn to sort of take it over. And then with climate change, there's really no dispute in terms of the actual science of it. But there is dispute just in terms of like society in general. And some of it can come from just political or monetary reasons. So like fossil fuel industry obviously has a reason to push back on climate change, say it's not happening. Same way with countries that rely on oil and fossil fuels to sort of support them. If we turn away from them, obviously they're going to be losing large amounts of money, so it's not going to be something that they want to do. So they obviously have the incentive to sort of what's the word I'm looking for? I don't want to say dispute because it's the word on here, but I'll just use it because I can't think of the word I'm trying for. But they have the reason to dispute climate change, just say it's not actually happening because they've got that financial incentive. But then just in terms of some of the other reasons that people may say is climate change, just if we want to address it, we're going to have to change our lives drastically, and there's actually no alternative to do it. Both of those can be just answered with clean energy. So if we can switch to greener, more renewable to energy sources, we don't really have to change our lifestyles too much because we're going to be able to produce that electricity that sort of supports our lifestyles. We're going to be able to produce that electricity clean and efficiently. And if we do invest in those types of energies, obviously then we will have the alternative to the current fossil fuels that we rely so heavily on. And then other ones are sort of related to different things we've seen in the past in terms of the climate. So some people say that solar variations explain the current warming we're seeing, which is incorrect just because the warming's too large for the solar variations to account for it on its own. And then they also bring up just the climate change that has occurred previously. Because again, climate change is a natural process, but the climate change we're seeing currently is accompanied by the highest carbon dioxide concentrations that were ever observed in the past million years. And with that, I'm saying observed to include the ice cores. So obviously we can measure directly the concentrations from the past 700 million years or so. But based on the ice cores, we could sort of back calculate it and get the concentration that way. But then also warming is currently occurring faster than just what was observed with natural fluctuations. And the temperature right now is pretty much at the highest it's ever been. And then other reasons, and again, I put reasons just because I put reasons in quotes because they're not actually good reasons. But some people sort of just confuse weather with climate. So if it's snowing, how can we be experiencing global warming if it's cold enough for it to snow? But again, that's just weather. That's not climate. And then other people point out that certain climate scientists may have made mistakes, but that doesn't dispute or refute entirely just the overall scope of the evidence. And that's why a lot of times when you see people arguing with climate scientists, they wind up arguing sort of with the scientists rather than with the argument. So they start arguing with that person rather than what that person's saying. And then with this, there are sort of a couple different types of solutions to climate change just in general. We're going to look at one of them, renewable energies, in a chapter later on. So we'll focus on the different types of energies, the different alternatives to the fossil fuels that we currently use so much. But with this, one thing to mention is that developing countries are currently investing quite a lot in the different types of renewable energy, so solar, wind, things like that. And then legislation is going to be one avenue for this. So there's different local and state initiatives. So California typically has a sort of a leading role in America in terms of adopting environmentally friendly laws and legislation. Things like the exhaust on cars having to be sort of meet a certain criteria, and then they sue different different car companies that didn't meet those standards just because they accuse them of being liable for the poor air quality that ultimately led to poor health in certain individuals. Similarly, there's the Paris Accord, which is just a UN agreement between a bunch of different countries with just a couple different sort of key points, ultimately trying to address climate change. With it, there are issues. It's not really enforceable, relies on countries to kind of police themselves. In some ways, you could agree to not trade with the other countries that aren't meeting these guidelines, meeting these steps towards addressing climate change. And that was one thing different countries threatened when Trump pulled out of the Paris Accord when he became president. But then Biden did rejoin the accord when he took over office. But with him, you can see the couple main points. Again, 1.5 degrees is what we're really focusing on. But 2 is kind of the upper limit of what it should be in terms of an allowable increase. Obviously, no increase is good, but that's kind of where we're at this point. And then with it, it's obviously going to cost a whole bunch of money. So they do have a plan to finance that money. The richest countries are going to sort of donate just $100 billion annually. And then depending on the country, there are just different goals to kind of address climate change as a whole. And then with it, we can think about, again, we're focusing on carbon emissions. What other people do is focus on it in sort of a wedge approach. So you can see each of these different wedges just referring to a sort of a different aspect, something we can do to improve the carbon emissions, because what the top line here is sort of the current projection if we don't do anything. And then the wedges are just how much we can reduce it if we make these different changes. So if we make vehicles more efficient, we can lower the carbon emissions by this much. If we make electricity more efficient, same idea. Protect forests and soil is going to reduce carbon by that much. And then if we do all of these together, that's where we're going to see this large scale change. So the wedge approach is good because you can kind of more easily focus on the different aspects, especially because this entire thing is probably unlikely, probably not going to get down to all the way at the bottom. But even if we could get 2/3 of the way there, even if we could do just like a few of these things, that would go a long way. Obviously, we want to do all of them, but just being thinking realistically, that's probably not going to happen, at least not for a while, I would guess. And then one other solution is just going to be carbon capture. So we talked about this a little bit in I think when we were looking at deforestation. But the way this works is essentially as the carbon dioxide, as those carbon emissions are being produced, we're just preventing them from getting into the atmosphere. And in some cases, what that's going to do is mean sort of diverting them for some other use. So I'm actually not familiar with what they would be used for in cement, but just some sort of mixing process, I would assume. And then in other cases, they actually just get pumped and stored underground. Because if they're underground, we're just not going to have the greenhouse effect. If they were to somehow leak out, obviously it would still occur. And then the opposite, when we're not having the carbon capture, is obviously we're just pumping those greenhouse gases just directly into the atmosphere. But with this, this is going to be a very, very expensive process. And I think in the deforestation part of the course, it said that the equivalent of carbon capture to just protecting the forest is carbon capture cost. I think it was $130 to remove whatever the amount of carbon dioxide was, whereas investing, I think it was less than $1 in protecting the forests would remove the same amount of carbon dioxide. So protecting the forest, protecting the environment just to begin with, is going to be a much cheaper option than trying to worry about it afterwards. And with that, I should say, protecting the forest and things like that, obviously the best. Then carbon capture, things like this would be the second best, because even this is going to be much cheaper than the cost of inaction in terms of just the environmental disasters that are going to sort of continue to occur, but also the negative health consequences that are going to result as well. So again, as we see the forest, the wildfires start to occur, we're going to be exposed to more harmful chemicals, or at least the people near those. So in addition to just the environmental consequences, there are the health consequences too. So doing nothing's going to, even though doing something is going to be expensive, doing nothing is going to be much more costly in the long run.